A telescope pointed at a patch of sky the size of a grain of sand held up at arm's length. And in that tiny slice, it found thousands of galaxies. Some of them had no right to exist. James Webb confirmed galaxies so massive, so structured, so alive with stars, that they predate everything our best models allow. We will visit impossible giants, dead galaxies that stopped living before our sun was even a thought, and a crisis that has cosmologists tearing apart 50 years of certainty. If you enjoy the journey, subscribe and leave a like. It keeps this going. Brace yourself. We begin. The image appeared on screens around the world on July 12, 2022, and the first people to see it went quiet. It was a deep field image, a tiny square of the universe, so small that if you held a grain of sand at arm's length against the night sky, that grain would cover it. And inside that square, packed into every corner, were thousands of galaxies, spirals, ellipticals, clusters twisted by gravity, all of them ancient, all of them staring back across billions of years of time. Scientists had seen deep field images before. The Hubble Space Telescope had produced them. Beautiful, stunning images that took days of exposure to capture. But this one was different. This one took James Webb 12 hours, and the detail it captured was sharper, deeper, and older than anything Hubble had ever touched. People cried. Actual researchers, people who had spent careers studying the cosmos, sat in front of their laptops and felt something crack open inside them. One astronomer described it as looking at the face of God. Another said it felt like the ground had shifted under their feet. But the emotion wasn't just about beauty. It was about what those galaxies implied. Some of the objects in that image were so far away that the light reaching the telescope had been traveling for over 13 billion years. The universe itself is only about 13.8 billion years old. So Webb was seeing things that existed when the universe was barely a few 100 million years old. Barely a toddler, cosmically speaking. And some of those things looked wrong. Galaxies take time to build. Gas has to cool. Gravity has to pull that gas into clumps. Those clumps have to collapse into stars. Stars have to live and die and seed space with heavier elements. And then slowly, over hundreds of millions of years, a galaxy starts to take shape. That is what the models say. That is what every cosmological simulation, every mathematical framework built over 5 decades of research had always told us. The galaxies in that image did not care about the models. Some of them were massive, fully formed, packed with stars, and they existed at a point in cosmic history when, according to our best understanding, they should have been barely getting started. A construction crew that was supposed to be pouring foundations had already built a skyscraper. In the days after the image dropped, researchers started pulling the data apart. They measured redshifts, the stretching of light caused by the expansion of the universe, to calculate how far away each object was. And the numbers kept coming back wrong. Wrong in the way that makes physicists reach for their notebooks and start questioning assumptions they had held for their entire careers. One team published a paper within weeks, then another, then another. The tone in those early papers was careful, measured, the language of scientists who know that extraordinary claims need extraordinary evidence. But underneath the careful language, the same word kept appearing. Impossible. It was a word that had no place in a scientific paper. A word that signals something has gone badly wrong, either in the data or in the theory. And in this case, the data kept checking out. The grain of sand had swallowed 50 years of certainty. And what those galaxies actually broke, the specific model, the specific prediction that collapsed under their weight, is the part that should genuinely unsettle you. For 50 years, cosmology had a backbone. It had a name that sounded technical, but described something straightforward: the Lambda CDM model. Lambda stood for dark energy, the force pushing the universe apart. CDM stood for cold dark matter, the invisible scaffolding around which all visible matter clusters. Together, they formed the standard model of cosmology, the closest thing the field had to a universal law. And it worked brilliantly. It explained why the universe looks the way it does today. It predicted the large-scale structure of space, the way galaxies form into filaments and sheets and walls, separated by enormous empty voids. It matched observations from multiple telescopes across multiple decades. Researchers ran computer simulations using its equations, and those simulations produced universes that looked almost identical to the one we actually live in. The model said the universe began with the Big Bang 13.8 billion years ago. For the first few 100,000 years, it was a hot, dense, opaque soup of energy and particles. Then it cooled. Hydrogen atoms formed. Light could finally travel, and darkness fell across the universe, a deep, cold, featureless dark that lasted hundreds of millions of years. Then gravity went to work. Tiny fluctuations in the density of matter, fluctuations so small they were essentially quantum ripples from the Big Bang itself, began to pull gas together. Slowly, the first structures were small, miniature halos of dark matter, invisible but massive, acting like gravitational anchors. Gas fell into those halos. It cooled. It collapsed. The first stars ignited. Those early stars were enormous and short-lived. They burned through their fuel fast and exploded, scattering heavy elements into space for the first time. New generations of stars formed from that enriched gas. And gradually, over hundreds of millions of years, the first true galaxies began to take shape. The word the model used was gradual, slow accumulation, bottom-up growth, small structures forming first, merging, growing, eventually becoming the massive galaxies we see today. The Milky Way, by this timeline, took billions of years to reach its current size. Every large galaxy did. That timeline was not a loose guess. It was backed by mathematics, by physics, by observations stretching across decades of telescope data. It was the most tested, most verified framework in the history of cosmology. And then Webb looked at the early universe and found galaxies that had skipped the line. The specific prediction that broke was this: at a point in cosmic history, less than 1 billion years after the Big Bang, galaxies should have been small, irregular, chaotic, still assembling. The model was precise about this. Large, massive, well-structured galaxies simply did not have enough time to exist that early. The universe had not given them the ingredients or the years required. Webb found them anyway, dozens of them, some holding more total stellar mass than the Milky Way holds today. Scientists did not immediately declare the model dead. Science does not work that way. They went looking for errors in the data first, because the model had earned that benefit of the doubt across 5 decades of success. Maybe the redshift measurements were off. Maybe the mass estimates were wrong. Maybe there was a systematic error buried in the telescope's calibration. They checked and checked again, and the galaxies stayed impossible. The model that had explained everything was suddenly struggling to explain what Webb was showing it. And Webb had barely started looking. What the telescope was actually built to do, and why its design made these discoveries inevitable, is where the real story of how we got here begins. Every telescope is a time machine. The farther it looks, the older the light it catches. But most time machines have a limit, a wall beyond which they go blind. For the Hubble Space Telescope, that wall was the very early universe. Hubble sees invisible light, the same light your eyes detect, plus a little into the ultraviolet and infrared. That range is extraordinary for studying galaxies and nebulae at moderate distances. But the most ancient light in the universe carries a problem. It has been traveling so long, across such vast expanding distances that the universe's expansion has stretched it completely out of the visible range. It arrives at a telescope as infrared light, invisible to Hubble, invisible to most instruments ever built. Webb was designed specifically to catch that stretched ancient light. Its primary mirror is over 21 feet across. Hubble's is just under 8 feet. That difference is enormous. A larger mirror collects more light, which means Webb can detect things far dimmer and far more distant than Hubble ever could. But size alone was only part of the solution. The mirror is made of 18 gold-plated beryllium segments, each one shaped to a precision measured in nanometers. Together they form a surface that focuses light with the accuracy that borders on the absurd. And crucially, the entire telescope operates at a temperature close to absolute zero, colder than the surface of Pluto, so that its own heat does not contaminate the infrared signals it is hunting. Webb sits nearly 1 million miles from Earth, parked at a gravitational balance point called Lagrange Point 2. At that location, the Sun, Earth, and Moon all sit on the same side of the telescope, allowing a massive sun shield the size of a tennis court to block all 3 heat sources simultaneously. Without that shield, Webb's own warmth would blind it to the faint infrared signals it was built to find. All of this engineering existed for one core purpose: to see the universe's first billion years. And the moment it pointed at the sky, it started finding things that surprised everyone. The surprise was not that Webb could see early galaxies. Scientists expected that. The surprise was what those galaxies looked like. The models had made specific predictions: small, irregular, still assembling. Webb found large, bright, structured objects, packed with stars, sitting at distances that placed them in the universe's infancy. Here is the scale of what that means. When Webb images a galaxy at a redshift of around 10 or higher, it is seeing light that left that galaxy when the universe was less than 500 million years old. For comparison, the universe today is nearly 14 billion years old. Webb is looking at a time so early that our Sun did not exist yet. The Milky Way did not exist yet. The solar system that carries every human being who ever lived did not exist yet. And in that ancient era, it found galaxies bigger and more developed than anyone predicted. The first specific galaxy candidate that stopped scientists mid-sentence was not some subtle blip in the data. It was bright, massive, and sitting exactly where the models said nothing like it should be. That discovery cracked the timeline open, and the crack only widened from there. The candidate had a catalogue name, a string of letters and numbers, so researchers simply called it one of the early monsters. It showed up in Webb's first batch of deep field data, and when the team ran the redshift numbers, the result came back at a distance, placing it around 300 to 400 million years after the Big Bang. At that age, the universe was still a teenager. Stars had barely begun populating the cosmos. The first galaxies, by every model humanity had built, should have been tiny, dim, and incomplete. This one was not tiny. Its estimated stellar mass put it in the range of a mature, fully developed galaxy. A system packed with billions of stars, all of them apparently already formed, already burning, already organized into a coherent structure. Sitting in a universe that had supposedly not given anything enough time to reach that state. The team that found it sat with the data for days before publishing. They ran the numbers again. They checked for gravitational lensing, the effect where a massive object between the galaxy and the telescope bends and magnifies the light, making something look bigger or brighter than it is. The lensing effect was minor. The galaxy was genuinely massive. They checked the redshift measurement from multiple angles using different spectral lines, different calibration methods. The answer kept coming back to the same era. This object existed when the universe was less than 5% of its current age. One researcher described the feeling as finding a fully grown adult skeleton inside the fossil record of the earliest single-celled life. The skeleton should not be there. Nothing in the evolutionary timeline allowed for it. But there it was, embedded in the rock. Undeniable. The mass of this galaxy, packed into such an early era, meant that star formation had to have been running at an extraordinary rate from almost the very beginning. They were forming at a pace the models assigned only to galaxies billions of years more mature. Somehow, in the chaos of the early universe, something had turbocharged the process. And this was just one galaxy. Within weeks of that first discovery, other teams began reporting similar objects from Webb's initial data set. Then, more. The early universe, which the models had described as a quiet nursery where small structures were just starting to flicker to life, was starting to look more like a factory running at full speed from day one. Scientists use a specific term for the total amount of stars a galaxy has formed over its lifetime. They call it stellar mass. The early monster galaxies Webb was finding had stellar masses that matched or exceeded galaxies we observe in the modern universe. Galaxies that had billions of years to build up that material. These ancient ones had done it in a cosmic eye blink. The standard explanation was missing, and the models that had survived every previous test were about to face the most serious challenge in the history of cosmology. But before anyone could explain what was wrong, scientists had to understand exactly what was in those galaxies, not just how massive they were, but what they were made of. That answer made the mystery considerably stranger. Star formation has a speed limit. At least, it used to. To make a star, you need a cloud of gas, primarily hydrogen, to cool down enough that gravity can pull it inward. As it collapses, it heats up. If it heats up too fast, the pressure from that heat pushes outward and stops the collapse. The process has a natural regulator built into the physics. Gas cannot fall inward faster than it can radiate heat away, and that radiating process takes time. Astrophysicists calculated this limit carefully. They gave it a name, the Eddington limit for star formation. They built it into every simulation, every model of galaxy evolution. It set a ceiling on how many stars a galaxy could produce per year. A galaxy like the Milky Way, for example, forms roughly 1 to 2 new stars per year today. Even during its most active periods, models suggested it would have maxed out at a few tens of stars per year. The early Webb galaxies appeared to be forming hundreds of stars per year. Some estimates pushed higher, in a galaxy that had only existed for a few 100 million years. To understand how extreme that is, picture a city that was supposed to take a century to build, but finished construction in 3 years, with every building already occupied and running. The construction crews worked day and night without stopping, somehow bypassing every logistical limit and material shortage that should have slowed them down. Scientists call this the efficiency problem. Galaxies in the early universe seemed to be converting their available gas into stars at an efficiency rate far above what the physics of cooling and collapse should allow. The models cap efficiency at a few percent, meaning only a small fraction of a gas cloud's mass ends up in stars, before feedback processes, supernovae explosions, radiation pressure, and stellar winds blow the rest away. The early galaxies Webb found appeared to be hitting efficiencies 5 to 10 times higher than that ceiling. One team ran simulations specifically trying to reproduce what Webb was seeing. They fed the simulation every boost they could think of. More dark matter, faster cooling rates, suppressed feedback. Even with every dial turned to maximum, they could not reproduce galaxies as massive as the ones Webb found. At those distances, within the laws of physics as currently understood. That last phrase is the one that carries weight. Within the laws of physics as currently understood, it left open a door. Either something in the early universe was operating under conditions different from what we assumed, or the physics itself had a gap in it that nobody had noticed yet. And there was one more ingredient making this stranger. When scientists looked at the chemical makeup of stars inside these early galaxies, they expected simplicity. The early universe was almost entirely hydrogen and helium. Heavier elements, carbon, oxygen, silicon, iron, form inside stars and get released when those stars explode. Building up a significant quantity of heavy elements takes generations of stars living and dying. These galaxies had them already. The presence of those heavier elements in structures so ancient meant that multiple generations of stars had already lived and died before these galaxies even appeared in Webb's data. A timeline stacking on top of a timeline, each layer making the gap between observation and theory wider. The next question was obvious. How does a galaxy even begin? And the answer to that question, pulled apart carefully, is where the entire framework starts to shake. Before Webb changed the picture, the story of galaxy formation was one of the most elegant things in science. It started with almost nothing. After the Big Bang, the universe was smooth, nearly perfectly smooth. But nearly is the word that matters. There were tiny variations in density, ripples so small they existed at the quantum scale, locked into the fabric of space from the universe's first fraction of a second. As the universe expanded and cooled, those ripples grew. Regions slightly denser than their surroundings pulled in more matter through gravity. Over millions of years, those overdense regions became the seeds of everything. Dark matter collapsed first. Dark matter does not interact with light and does not heat up the way normal matter does. So it could start collapsing much earlier. It formed invisible halos, gravitational wells spread across space, waiting to catch the gas that would eventually fall in. Scientists call this the cosmic web, a three-dimensional lattice of dark matter filaments with dense nodes where the filaments meet. Every major galaxy in the universe today sits inside one of those nodes. Normal matter, hydrogen, and helium gas followed. It fell into the dark matter halos, heated up as it compressed, and began radiating that heat away. As it cooled, it sank toward the center of the halo and started fragmenting into smaller clouds. Those clouds collapsed further. The densest cores of those clouds, under enough gravitational pressure, ignited nuclear fusion. The first stars were born. Those first stars were monstrous, potentially hundreds of times more massive than the sun, burning blue and white and hot, consuming their fuel in a few million years before exploding as supernovae. Those explosions seeded the surrounding gas with the first heavy elements, and the shock waves compressed nearby gas clouds, triggering new rounds of star formation, generation after generation, each one enriching the gas further, building complexity out of simplicity. Over hundreds of millions of years, multiple stellar generations inside a single halo produced the beginnings of a true galaxy. Disk structures formed as the gas settled into rotation. Central bulges grew as stars accumulated near the core. Spiral arms developed from density waves moving through the disk. Mergers added mass. When two halos and their galaxies collided, they merged into something larger. Over billions of years, small galaxies merged into medium ones, and medium ones merged into large ones. The Milky Way itself bears the scars of past collisions. Streams of stars pulled from smaller galaxies absorbed long ago. This entire process had a pace baked into it by physics. Gas cooling rates, gravitational freefall timescales, the speed at which shock waves travel. These are not flexible numbers. They set a clock that no galaxy could outrun. That clock said a galaxy the size of the Milky Way needed billions of years to reach its current state. Not a few 100 million. Billions. Webb found galaxies matching the Milky Way's mass before the clock had ticked past 500 million years. Somewhere between the elegant theory and the telescope data, something fundamental was missing. A piece of the process that nobody had accounted for. or a piece that did not behave the way anyone expected. Some scientists began pointing at the universe's first stars, the ones no telescope had ever directly seen, as the hidden variable. And the closer researchers looked at those stars, the stranger the picture became. In early 2023, a team of astronomers published a paper that landed like a punch. They had identified 6 galaxy candidates from Webb's early data and confirmed their distances using careful spectroscopic analysis. All 6 sat at redshifts placing them in the universe's first 700 million years. All 6 had stellar masses that the models said were flat out impossible for their age. The largest of them held a mass roughly equal to the Milky Way today. Our galaxy is 13 billion years old and took that entire span to accumulate its stars. This object had done the same in less than 700 million years. If you compress the Milky Way's entire formation history into a single human lifetime, this galaxy finished the job before the person reached their 5th birthday. The team was led by an astronomer named Ivo Labi, and when the results came in, his response became one of the most quoted lines in recent cosmology. He said the findings were so unexpected that they caused genuine stress. The word he used in interviews was panic. The scientific community did not panic visibly, but it moved fast. Other teams immediately began scrutinizing the data, hunting for errors, alternative explanations, anything that could resolve the tension without dismantling the standard model. One early suggestion was contamination. Some objects at moderate distances can mimic the photometric signatures of very high redshift galaxies if the measurements are imprecise. Webb's photometric redshifts, the quick estimates made from brightness at different wavelengths, are extraordinarily good, but not perfect. Maybe these objects were closer than they appeared, appearing massive because they were nearby, not because they were genuinely enormous. Spectroscopic confirmation, the gold standard of distance measurement, addressed that concern for several of the candidates. The confirmed ones held their distance. They stayed impossible. Another suggestion was that the stellar mass estimates were wrong. Calculating how much total mass a galaxy holds in stars requires assumptions about the stellar population, the mix of star sizes and ages. If the early galaxies had an unusual overabundance of very massive stars, the models used to calculate total mass could overestimate the answer. A team in the United Kingdom ran through the numbers, assuming an extreme stellar population skewed heavily toward massive stars. The galaxies shrank somewhat, enough to ease the tension for 2 of the 6. The other 4 stayed above what the models allowed. The size of those 4 remaining galaxies and the dozens of similar candidates that continued to accumulate in Webb's growing dataset pointed at something structural. A single anomaly can be explained away. A statistical pattern cannot. Researchers started using a specific phrase to describe what was happening. They called it tension with the standard model. In the language of physics, tension is a polite word. It means 2 things that should agree are disagreeing, and the gap between them is large enough that it cannot be ignored. The tension here was not small. The galaxy masses Webb was finding exceeded model predictions by factors of 10 to 100. That is not a rounding error. That is a chasm. And the chasm had a particular quality to it. Every solution proposed to close it from one side opened a new problem somewhere else. Patch one hole and another appeared. The models were holding together, but only barely, and the patches were starting to look more desperate than convincing. Something stranger was embedded in the light of those galaxies, something about their chemical composition that made the whole problem more layered than anyone expected. There is a period in the universe's history that cosmologists call the Cosmic Dark Ages. After the Big Bang's initial fireball cooled, and before the first stars ignited, the universe sat in darkness, complete, absolute darkness. No light sources existed. The cosmos was filled with neutral hydrogen gas, cold and inert, absorbing any stray photons that tried to pass through it. For somewhere between 100 million and 400 million years, nothing glowed. Then, somewhere in that darkness, the first stars switched on. Astronomers call that moment cosmic dawn, the point when light returned to the universe for the first time since the Big Bang's glow faded. It was the beginning of the process called reionization, when the radiation pouring out of the first stars slowly burned through the surrounding neutral hydrogen, ionizing it, clearing the fog that had blanketed the cosmos. Before Webb, cosmic dawn was theoretical territory. Researchers could calculate when it should have happened. They could see its after effects in the light of distant quasars, where the hydrogen fog had left specific absorption signatures. But seeing the actual sources of that first light, the very first galaxies and stars igniting in the dark, was beyond any instrument ever built. Webb pushed into that era for the first time. The images it captured from the epoch of reionization showed galaxies in the process of punching holes in the surrounding hydrogen fog. Bright knots of young stars radiating ultraviolet light so intense it could strip electrons from hydrogen atoms at distances of hundreds of light years. Small, chaotic, irregular structures, some of them, yes, but also, sitting alongside the small ones, the large impossible ones that had no business being there. Seeing cosmic dawn directly changes something fundamental about how cosmology works. Before Webb, that error existed only in theory and indirect measurement. Now there is data from it. Actual photons that left actual galaxies during the universe's first few 100 million years, hitting a mirror in space and producing images a team of engineers and scientists can hold on their screens. The reionization process itself appears to have been patchy and complex, driven by clusters of early galaxies working together to clear the hydrogen fog in their surrounding regions, before other regions caught up. Webb's data is revealing that patchiness in real time, mapping which areas of the early universe cleared first and why. But the most striking revelation from cosmic dawn is what it implies about the pace of everything. The galaxies clearing that fog, ionizing that hydrogen, were doing so at an energy output that requires enormous numbers of young, hot, massive stars. Enormous numbers that, given the age of those galaxies, imply star formation rates that the models did not predict. Cosmic dawn arrived earlier and burned brighter than anyone expected. And underneath all of that brightness, underneath all of those stars and galaxies and that ionizing radiation, was a deeper question that Webb's data had not yet answered. How does a universe go from perfect darkness to thousands of fully formed galaxies in a span of time that, cosmically speaking, barely registers as a pause? The tool scientists use to peel back that timeline relies on a property of light so elegant it borders on poetry, though in this case it is pure physics. Every galaxy in the universe is moving away from every other galaxy. The universe is expanding, and that expansion stretches the space between objects, like pulling taffy. Light traveling across that expanding space gets stretched along with it. The wavelength of the light increases. It shifts toward the red end of the spectrum. Astronomers call this redshift. The farther away a galaxy is, the more space the light has crossed, and the more that light has been stretched. A galaxy close to us shows a small redshift. A galaxy at the edge of the observable universe shows an extreme redshift, its original ultraviolet light stretched so far that it arrives as infrared radiation. Redshift is a number. The higher the number, the more ancient the light. A redshift of 1 means the universe was about half its current size when that light was emitted. A redshift of 10 means the universe was roughly 1/30th of its current size, corresponding to a time less than 500 million years after the Big Bang. A redshift of 20 or higher puts you at the universe's first 200 million years. Webb was designed to read those extreme redshifts because its instruments are tuned to the infrared wavelengths where that ancient, heavily stretched light arrives. There are two ways to measure redshift. The first is photometric, where researchers measure how bright a galaxy appears at different infrared wavelengths and use those brightness patterns to estimate the redshift. It is fast and can be applied to thousands of galaxies at once, but it carries uncertainty. The second method is spectroscopic, where the telescope disperses the galaxy's light into a detailed spectrum and reads specific absorption or emission lines at known wavelengths. Those lines, shifted by a precise amount, give a highly accurate redshift measurement. Webb can do both. Its photometric capability allowed researchers to rapidly identify hundreds of high redshift candidates in its earliest data. Its spectroscopic instruments then confirmed the most extreme cases, nailing down distances with the precision that photometry alone could not achieve. Before Webb, the highest confirmed galaxy redshift sat around 11, corresponding to a time about 400 million years after the Big Bang. That was the edge of the known observable universe, the furthest back any telescope had directly confirmed a galaxy. Within its first year of operation, Webb confirmed galaxies at redshifts above 13. Then teams reported candidates above 16. Each new record pushed the confirmed window of observation deeper into the universe's infancy, and each new galaxy sitting in that window added weight to the growing problem with the models. The precision of Webb's redshift measurements also addressed one of the main escape hatches that skeptics had used to resist the early reports. If the redshifts were wrong, the galaxies could be closer, smaller, and perfectly consistent with the standard model. Webb's spectroscopic confirmations closed that escape route, one galaxy at a time. The light had traveled across billions of years to reach the mirror. The mirror had measured it with enough accuracy to confirm a crisis. And that crisis had specific numbers attached to it. Numbers that, once laid out plainly, make the scale of the problem impossible to minimize. The paper dropped in February 2023, and the cosmology community spent the following weeks dissecting every line of it. 6 galaxies, all confirmed distances placing them within the universe's first 700 million years, all carrying stellar masses that, under the standard model's predictions, required timescales of several billion years to accumulate. The most extreme of them held a mass equivalent to roughly 100 billion times the mass of our Sun. 100 billion solar masses, packed into a galaxy that had, at most, 700 million years to form. To put that in physical terms, if you laid every star in the Milky Way end to end, the line would stretch for an almost incomprehensible distance. These galaxies held comparable numbers of stars, all formed in a window of time shorter than the current age of many individual stars that exist today. Some stars alive right now in our own galaxy are older than the entire formation period those ancient galaxies had available. The team behind the paper was careful. They walked through each alternative explanation methodically and documented why each one fell short. Contamination by closer objects at lower redshifts, addressed. Unusual dust distributions affecting mass estimates, addressed. Systematic errors in Webb's photometric calibration, addressed. At each step, the galaxies held their ground. The paper's conclusion was stated in deliberately restrained scientific language, but the meaning was clear. Either the standard model of galaxy formation was missing a critical physical process, or the parameters of cosmology itself needed revision. A cosmologist from MIT described the findings publicly as a potential 5 sigma tension with theoretical predictions. In statistics, 5 sigma means the probability that the result occurred by chance is less than 1 in 3.5 million. That threshold is the gold standard for a genuine discovery, or in this case, a genuine problem. Other researchers pushed back, as science requires. Some argued that the mass estimates for early galaxies are inherently uncertain because scientists must make assumptions about what kinds of stars those galaxies contain. A galaxy packed predominantly with very massive, short-lived stars would look brighter than expected for its actual total mass, leading researchers to overestimate how many stars it had. This argument had merit in some cases, but when the corrections were applied, several of the six held their impossible masses, and they were joined by dozens of additional candidates, accumulating in Webb's expanding datasets. The scale of the discrepancy also resisted the calibration error explanation. An error large enough to explain away 100 billion solar masses would have to be catastrophically large enough that Webb's engineering team would almost certainly have caught it in testing. The telescope's calibration had been verified against known standard candles before it ever pointed at the deep field. 6 galaxies became a reference point. Researchers began calling them the Impossible Six in informal conversations, though no paper used that phrase. They represented the moment when the tension between Webb's observations and the standard model crossed from interesting anomaly into active crisis requiring resolution. And buried in the chemical fingerprints of those galaxies was another layer of the problem entirely, one that pointed backward in time even further than the galaxies themselves. The early universe was chemically simple, staggeringly simple by the standards of the cosmos today. In the first few minutes after the Big Bang, nuclear reactions fused protons and neutrons into the lightest elements: hydrogen, helium, and trace amounts of lithium. That was it. The entire periodic table from carbon to gold to uranium did not exist yet. Every heavy element in the universe had to be built inside stars and released into space when those stars died. This process has a name: stellar nucleosynthesis. Stars fuse hydrogen into helium in their cores. As they age, they fuse helium into carbon and oxygen. The most massive stars continue up the periodic table, producing silicon, sulfur, and eventually iron. When those massive stars explode as supernovae, they scatter those elements into the surrounding gas, and in the extreme conditions of the explosion itself, elements heavier than iron form through rapid neutron capture. Building up a meaningful supply of heavy elements in the gas surrounding a galaxy takes time. First, massive stars have to form. Then they have to age and die, a process taking anywhere from a few million to tens of millions of years for the most massive ones. Their debris has to mix into the surrounding gas. New generations of stars have to form from that enriched gas and repeat the cycle. Each round enriches the chemical environment slightly more. Multiple generations of stars, living and dying, are required before you see significant concentrations of heavy elements. Cosmologists track this chemical enrichment as a clock, a secondary way of estimating how long a galaxy has been actively forming stars. The early Webb galaxies showed levels of chemical enrichment that implied those multiple generations had already completed. Carbon, oxygen, and other processed elements appeared in the spectra of galaxies sitting at redshifts corresponding to the universe's first few 100 million years. That enrichment tells a story. Before those visible galaxies appeared in Webb's data, an earlier generation of stars had to have lived and died, an unseen generation, or several, whose existence we can only infer from the chemical legacy they left behind in the gas. It is like finding a village with buildings made of bricks, in a region where no one has yet seen a kiln. The bricks prove the kiln existed. You just have not found it yet. For cosmologists, this implied that significant star formation activity, possibly intense activity, was occurring even earlier than the galaxies Webb was directly observing. The timeline of cosmic dawn, already being pushed backward by Webb's discoveries, potentially stretched even further into the dark. Some researchers began considering whether the very first generation of stars, the ones theorized to have ignited just a few 100 million years after the Big Bang, could have been responsible. Those theoretical first stars had properties so extreme that they operated by different rules than any star alive today, and the question of whether Webb would eventually see one, and what it would find, had already become one of the most watched races in modern astronomy. But before those first stars, there was a deeper infrastructure at work, an invisible architecture that shaped where every star and galaxy would ever form. Understanding it is key to understanding why the early universe might have been able to build galaxies so fast. Cosmologists gave them a name before anyone had ever seen one. Population 3 stars. Population 1 stars are young stars like our Sun, formed from gas already enriched with heavy elements. Population 2 stars are older, formed from less enriched gas, born in the universe's Middle Ages. Population 3 stars are the theoretical first generation, formed from the raw, pristine hydrogen and helium of the early universe, with essentially no heavy elements at all. Those 3 words, no heavy elements, carry enormous consequences. Heavy elements act as cooling agents in collapsing gas clouds. When gas collapses to form a star, heavy elements radiate heat away efficiently, allowing the cloud to keep shrinking and break into smaller pieces. That fragmentation is what produces the wide range of star sizes we see today, from tiny red dwarfs to massive blue giants. Without heavy elements, gas cannot cool as efficiently. Instead of fragmenting, it stays as one large collapsing mass. The prediction is that population 3 stars were enormous. Some models suggest individual stars could have held anywhere from 100 to perhaps 1,000 times the mass of our Sun. Stars that large burn at temperatures and luminosities so extreme that they would look nothing like any star alive today. They would blaze blue-white, radiating energy at a rate that consumed their entire fuel supply in just a few million years before exploding in supernovae powerful enough to scatter heavy elements across thousands of light years. In their brief, violent lives, these stars would have poured out ionizing radiation at a ferocious rate. A single population 3 star, burning at full intensity, would have ionized more hydrogen per second than entire clusters of modern stars. They were the original engines of reionization, the fires that lit up the cosmic dark ages. And their deaths seeded the universe with the first heavy elements, triggering the next generation of star formation in enriched gas, and setting off the chain reaction of increasing chemical complexity that eventually produced planets, oceans, and living organisms. No population 3 star has ever been confirmed directly. They burned out billions of years ago, but the chemical signatures they left behind, the specific patterns of element abundances in very old stars and ancient gas clouds, have been used to infer their properties with increasing confidence. Webb's ability to peer into the epoch of reionization has raised hopes that a direct detection might be possible. Some models suggest that the most extreme population 3 stars would produce such powerful ionizing radiation that their signature could survive in the spectra of early galaxies, even if the individual stars themselves cannot be resolved. A few candidate signals have appeared in Webb's data. Unusual emission lines in the spectra of some high redshift galaxies suggest radiation fields more intense and harder than any modern star cluster could produce. Those signals could be population 3 stars still active at early cosmic times, or they could be something else entirely. The answer is not yet confirmed. Science marks this as an open, actively investigated question, but whether or not population 3 stars are directly visible, their influence on the early universe appears to have been staggering, and that influence connects directly to a problem that goes beyond star formation rates and chemical enrichment, a problem that sits at the very heart of how mass accumulates in the early cosmos. Physics places limits on how fast things can happen. Gravity pulls matter together, but gravity has to fight against pressure, heat, and the random motion of particles. Star formation is a competition between those forces, and the competition has an outcome baked into the physics. Only a small fraction of a gas cloud's mass ends up in stars. Astronomers quantify this as star formation efficiency. In the local universe today, the efficiency is low, roughly 1 to a few %. A gas cloud of a given mass will convert just a tiny fraction of that mass into stars before stellar feedback, the radiation, winds, and explosions from newly formed stars disperses the remaining gas and shuts the process down. That low efficiency is why the Milky Way forms only 1 or 2 new stars per year, despite being a galaxy of hundreds of billions of stars. The raw material exists, but physics throttles the conversion rate. The standard model built that throttle into every simulation. It was not an assumption scientists forgot to question. It came directly from observations of star-forming regions in nearby galaxies, checked against decades of data. Low efficiency was the rule. Webb's early galaxies appeared to be operating at efficiencies 5 to 10 times higher, possibly more. The amount of stellar mass packed into those galaxies relative to the total gas available in the early universe was simply too large to produce at standard efficiency rates within the available time. One team tried to quantify exactly how extreme the problem was. They calculated the total stellar mass in Webb's confirmed high redshift massive galaxies and compared it to the total amount of normal matter, meaning hydrogen and helium gas, that cosmological models predicted should have been available in those regions of space at that time. In several cases, the stellar mass in the galaxies appeared to account for more than half of all the available normal matter in that cosmic volume, half of all available gas converted into stars in a few 100 million years, when the local universe today, across billions of years, has converted only about 5% of available gas into stars across all of cosmic history. That comparison makes the efficiency problem concrete and severe. Something in the early universe either made gas collapse faster, cooled it more efficiently, or prevented the feedback processes from shutting star formation down. Possibly all three. Several mechanisms have been proposed. Turbulent compression, where large-scale gas flows in the early universe drove density spikes that overwhelmed the normal feedback threshold. Cosmic rays from the first supernovae seeding magnetic fields that channeled gas towards star-forming regions more efficiently. The extreme density of the early universe providing gravitational compression from all directions simultaneously. Each mechanism is plausible in isolation. None of them, alone or combined in current models, fully closes the efficiency gap. The search for the missing mechanism pointed researchers toward a suspect that had been lurking in the background of galaxy formation theory for decades, one whose role in the early universe had always been underappreciated. And once scientists started looking at it seriously, the picture shifted in directions no one had fully anticipated. Dark matter is the most abundant form of matter in the universe. It makes up roughly 85% of all matter, vastly outweighing the normal matter that makes up stars, planets, gas, and every physical object ever observed directly. Yet, it has never been directly detected. It emits no light, reflects no light. Its existence is confirmed entirely through its gravitational effects on visible matter. Those gravitational effects are profound. Galaxies rotate too fast at their edges for their visible mass to account for. Clusters of galaxies bend light from objects behind them more strongly than visible matter alone could explain. The large-scale structure of the universe, that cosmic web of filaments and voids, matches perfectly with simulations that include dark matter and falls apart without it. So dark matter is real, almost certainly, but what it actually is, what particle or field or fundamental entity it consists of, remains completely unknown. This is confirmed as an active, unsolved problem in physics. In galaxy formation models, dark matter plays the anchor role. Gas falls into dark matter halos. Stars form from that gas. Galaxies grow within those halos. The properties of dark matter, specifically that it is cold, meaning it moves slowly relative to the speed of light, determine the scale at which those halos form and the rate at which they grow. Cold dark matter halos grow hierarchically, bottom up. Small halos form first, then merge into larger ones. The pace of that merging sets the pace of galaxy growth, and the pace locked into the Standard Model's cold dark matter framework produces galaxies growing slowly, matching observations of the universe in its middle and later ages. Webb's massive early galaxies challenged whether that framework applies cleanly to the earliest cosmic times. If dark matter halos in the early universe were somehow more concentrated than the models assumed, more efficient at pulling gas inward, they could have accelerated star formation beyond the predicted limits. Some researchers began proposing modifications to the nature of dark matter itself. What if early dark matter halos were more compact than cold dark matter models predict? What if dark matter had a small but non-zero interaction with normal matter at early times, providing an extra mechanism to funnel gas towards star-forming regions? Other proposals suggested that dark matter might have different properties at different energy scales. A warm dark matter variation, where particles move faster, would produce a different halo structure in the early universe and potentially concentrate matter differently. These are theories, not confirmed findings. The honest scientific position is that cold dark matter remains the best supported model overall, and the modifications needed to explain Webb's early galaxies are speculative. But the fact that modifications are being seriously discussed in peer-reviewed literature signals how significant the tension has become. And there is another player in the early universe, one with perhaps even more dramatic potential to explain the impossible galaxies. A player that sits at the center of every massive galaxy today, including our own, and whose behavior in the early universe may have been far more extreme than anything observed in the modern cosmos. At the center of virtually every massive galaxy in the observable universe sits a supermassive black hole. The Milky Way's central black hole holds a mass 4 million times that of the Sun. The largest known supermassive black holes weigh in at tens of billions of solar masses. They are not exceptions. They appear to be a fundamental feature of how large galaxies are built. The relationship between a galaxy's total mass and the mass of its central black hole follows a surprisingly tight correlation. More massive galaxy, more massive black hole. The two seem to grow together, locked in a feedback relationship where each influences the other's development. Scientists call this co-evolution, and understanding it has been one of the central projects of galaxy formation research for 2 decades. Before Webb, the standard picture of co-evolution assumed it played out over billions of years. Galaxy builds up mass, black hole at its center grows by eating gas and stars, and the energy released by that feeding regulates star formation, sometimes suppressing it, sometimes triggering it, depending on conditions. A slow, intertwined dance spread across cosmic history. Webb found supermassive black holes in the early universe that broke this timeline as thoroughly as the impossible galaxies themselves. Some high redshift galaxies observed by Webb contain black holes already holding hundreds of millions or even billions of solar masses, sitting at the centers of galaxies that have barely existed for a few 100 million years. For a black hole to grow to that size, it would have to start from a seed black hole of some minimum initial mass and accrete material essentially continuously at or near the maximum feeding rate allowed by physics from the universe's first moments. Even at maximum feeding rates, growing a billion solar mass black hole in a few 100 million years strains the standard picture severely. The only way it works within known physics is if the seed black hole started with very high initial masses, perhaps thousands or tens of thousands of solar masses, far larger than the black holes produced by ordinary stellar collapses today. Those hypothetical high-mass seeds have a name: direct collapse black holes. The theory proposes that in the early universe, under specific conditions of intense radiation and high gas temperatures, entire massive gas clouds collapse directly into black holes without forming stars first. skipping the stellar stage entirely, producing black hole seeds large enough to reach supermassive status on the observed timeline. Direct collapse is theoretically possible, but has never been confirmed. It requires a very specific set of environmental conditions that cosmologists are still working to verify existed in sufficient abundance in the early universe. What makes this connection to Webb's impossible galaxies significant is the feedback mechanism. A rapidly accreting supermassive black hole, called a quasar, pours out energy equivalent to trillions of suns combined. That energy can compress surrounding gas, triggering intense bursts of star formation in the host galaxy. A black hole feeding at extreme rates in the early universe could, in principle, drive the star formation rates Webb is observing in those massive early galaxies. If that mechanism was at work, then the impossibly massive early galaxies and the unexpectedly massive early black holes might be two symptoms of the same underlying condition. Understanding what that condition was, and whether current cosmological models can absorb it, became the central question of a formal, organized scientific response that reached all the way to the foundations of the field. Science does not abandon successful theories easily. It should not. 50 years of successful predictions earn genuine loyalty, and the history of science is littered with premature announcements of paradigm shifts that turned out to be instrument errors or miscalculations. The instinct to defend a well-tested model against new data is not dogmatism. It is appropriate caution. But by late 2023 and into 2024, the accumulation of Webb data had crossed a threshold that even the most cautious defenders of the standard model acknowledged publicly. The tension was systemic, consistent across independent teams, independent analysis methods. The word tension, in the formal literature, was giving way in some papers to something closer to challenge. The lambda CDM model did not collapse. That is important to state clearly. The vast majority of cosmological observations still match its predictions beautifully, including the detailed structure of the cosmic microwave background, the distribution of galaxies at moderate redshifts, and the large-scale web of cosmic structure. The model's overall architecture remained standing. What was failing was a specific sector of its predictions, the formation history of massive galaxies at very high redshift. The model predicted small, assembling structures. Webb found large, complete ones, and the gap between those two things did not shrink as more data arrived. It widened. In response, a series of formal workshops and review papers appeared, bringing together galaxy formation theorists, observational cosmologists, and particle physicists to assess the situation. The goal was to identify which parameters in the standard model could be modified to accommodate Webb's findings without breaking everything the model had already successfully explained. Several modifications emerged as candidates. The first involved tweaking the assumptions about how efficiently early galaxies converted gas into stars. If the models had systematically underestimated that efficiency, perhaps due to inadequate treatment of gas dynamics at very high redshifts, the problem could shrink. Critics noted that the underestimation required to close the gap was itself larger than any physically motivated correction. The second involved changes to the assumed initial mass function of stars in the early universe. If early stars were systematically more massive than stars today, a galaxy would produce more total luminosity per unit of stellar mass, making it appear more massive than it actually is. A systematic overestimate of galaxy masses could ease the tension for some objects. The third category went deeper. A small but serious community of researchers began proposing that the parameters of cosmology itself might need adjustment. The expansion rate of the universe, a value called the Hubble constant, has been under independent scrutiny since before Webb launched. Different measurement methods produce slightly different values for it, a discrepancy called the Hubble tension. Some theorists propose that a modified expansion history in the early universe could affect the timing of structure formation in ways that would make the impossible galaxies less impossible. None of these proposals produced a complete solution. Each one eased some part of the problem while leaving others unresolved. And each one pointed in the same direction. The early universe behaved differently than the models assumed, and the differences were not trivial. The review process also turned attention toward what Webb had not yet fully explored: the complete picture of what those early galaxies were made of, how their light had traveled to reach us, and what other surprises might be buried in the data already collected. Every galaxy is a library. The light it emits carries the combined history of every star that ever formed inside it. Encoded in that light are the temperatures, ages, chemical abundances, and evolutionary stages of stellar populations that lived and died billions of years ago. Astronomers developed techniques over decades to decode that information, turning the spectrum of a galaxy into a biography of its stellar history. This field is called stellar population synthesis. A team builds a model galaxy by combining the light profiles of stars at different ages and chemical compositions, adjusting the mix until the model's combined light matches what the telescope actually observed. When the match is good, the model reveals not just how many stars exist in the galaxy today, but when most of them formed, how metal-rich they were, and whether star formation has been steady or explosive. For the early Webb galaxies, this technique delivered results that added a new dimension to the crisis. Several of the massive high redshift galaxies showed stellar populations dominated by old stars. Old, in this context, is relative, since the entire universe was young. But the light profiles indicated that these galaxies had experienced their primary burst of star formation even earlier than the epoch being directly observed. The stars inside them were already aging when Webb caught them on camera. That pushed the timeline back another step. Researchers were already struggling to explain how massive galaxies existed at redshifts above 10. Now the data suggested those galaxies had their main star-forming episode at redshifts above 15, perhaps higher, in an era even Webb could barely reach. A team analyzing one particular galaxy in detail found that its stellar population synthesis pointed to a formation redshift possibly as high as 20. That corresponds to a time less than 200 million years after the Big Bang. At that point, the universe was not just young. It was almost entirely dark, still deep in the cosmic dark ages, supposedly years away from the first stars lighting up. A galaxy forming at redshift 20 would require the entire apparatus of structure formation, dark matter halo collapse, gas cooling, first star formation, chemical enrichment, and galaxy assembly to have run its course in a window so small that the standard model's timescales break down entirely. Stellar population synthesis also revealed something about the rate of chemical enrichment in these ancient galaxies. The heavy element abundances inside some of them were surprisingly high, suggesting that whatever stellar generations preceded them had been both numerous and short-lived, meaning they were massive stars that burned fast and scattered metals at scale. This paints a specific picture of the early universe as an extraordinarily active environment. More active, more productive, and more chemically complex at earlier times than the standard model predicted. An environment where the rules of gradual assembly either did not apply or were being overridden by processes that current physics has not fully characterized. The scale of what was missing from the model was becoming clear, and the deeper Webb looked, the more it found galaxies that had somehow grown old before the universe itself was old enough for that to be possible. What the telescope would find next, in the same datasets, pointed at a possibility so counterintuitive that it forced cosmologists to ask a question no one had seriously entertained in decades. The age of the universe is one of the most precisely measured numbers in science. 13.8 billion years, derived from multiple independent methods cross-checked against each other, refined over decades. The cosmic microwave background, the afterglow of the Big Bang, gives us that number with extraordinary precision. The expansion rate of the universe, measured across billions of light-years of galaxy motion, confirms it. The ages of the oldest stars in our galaxy, calculated from their chemical compositions and brightness, match it. 13.8 billion years has the kind of support that makes scientists comfortable, settled not in the lazy sense, but in the rigorous sense, tested from every angle and holding firm. So when a handful of researchers began quietly raising the question of whether that number might be wrong, the response from the broader community was skeptical, appropriately so. The argument went like this: Webb's impossible galaxies require so much early structure formation, so much stellar mass accumulated so fast, that even pushing every known physical mechanism to its limit cannot fully explain them within the standard timeline. One way to ease the pressure would be to give the universe more time. If the universe is older than 13.8 billion years, say 15 or 16 billion years, the early galaxies would have had more time to build up their mass before Webb observed them. This is a theory, stated clearly. Mainstream cosmology does not support it, and the evidence for the standard age is strong. But several papers, appearing in reputable journals, explored the mathematics of an older universe and found that specific modifications to early universe physics could, in principle, accommodate both the standard cosmic microwave background observations and an extended pre-recombination period that effectively lengthened the timeline available for structure formation. One physicist, Rajendra Gupta, from the University of Ottawa, published a paper in 2023 arguing that combining a model of evolving physical constants with a revised expansion history could push the universe's age to around 26.7 billion years. The paper attracted significant media attention and significant scientific criticism. Most cosmologists found the proposed modifications too unconstrained, meaning the model could be tuned to produce almost any desired result, which made it scientifically weak. The honest position is this: the universe's age, as currently measured, is robust, but the tension Webb has introduced opens a conversation about whether specific parameters in the early universe behaved exactly as the standard model assumes. Small modifications to early expansion dynamics, even ones that do not dramatically change the total age, could meaningfully affect how much time was available for structure formation in the first billion years. Some physicists began examining whether the early universe went through phases of accelerated expansion beyond the known inflationary period. Brief episodes that could have compressed the effective timescale for structure formation, giving matter more opportunities to cluster than the standard timeline suggests. Each proposal came with its own set of problems and its own set of defenders. The field was not converging on a single answer. It was fragmenting into competing hypotheses, each trying to account for the same stubborn observations from a different direction. And underneath all of them was a common thread. Something about the early universe was fundamentally more active, more structured, and more mature than the models allowed. Whether the fix was a longer timeline, modified dark matter, enhanced star formation efficiency, or something else entirely, the destination was the same. The early universe was a place where things happened faster than anyone had planned for. But there was one discovery in Webb's data that reframed the problem in a direction nobody expected. Galaxies that had stopped completely before they should have had any reason to. Dark energy is the name scientists gave to the force accelerating the universe's expansion. It was discovered in 1998 by two independent teams studying distant supernovae, and it earned its discoverers the Nobel Prize in Physics. The finding was shocking at the time. The universe was not just expanding, it was expanding faster and faster, pushed by some invisible energy field pervading all of space. That energy field dark energy makes up roughly 68% of the total energy content of the universe. It dwarfs dark matter, which itself dwarfs normal matter. In the Standard Model, dark energy is described by a single number called the cosmological constant, represented by the Greek letter lambda. That constant is assumed to be exactly that, constant, uniform across all of space, unchanging across all of time, a fixed background pressure pushing the cosmos apart at a steady, predictable rate. That assumption has worked well for explaining the universe's expansion history at moderate to late cosmic times. Observations of supernovae, galaxy clustering, and the cosmic microwave background all fit a universe with a stable cosmological constant. But Webb's findings about the early universe, combined with independent data from other telescopes, began raising a different question. What if dark energy was not constant in the very early universe? What if it had a different value or behaved differently in the first billion years after the Big Bang? A varying dark energy, called quintessence in some theoretical frameworks, would change the expansion rate of the early universe relative to what the Standard Model assumes. A different expansion rate in the early universe would change the rate at which matter clumped together under gravity, and a different clumping rate would change the timeline of galaxy formation. In early 2024, a major result from a project called the Dark Energy Spectroscopic Instrument, an enormous survey mapping the three-dimensional positions of millions of galaxies, suggested that dark energy may have varied over cosmic history. The data showed a slight preference for a dark energy that was stronger in the past and has weakened over time. The result was not definitive, sitting at a statistical significance where it could still be a fluctuation in the data, but it was consistent with other hints accumulating from multiple independent sources. If dark energy was stronger in the early universe, it would have pushed the expansion rate higher at early times. A faster expansion in the early universe would have meant that the seeds of structure, those quantum ripples from the Big Bang, were pulled apart more quickly, potentially producing a different pattern of galaxy formation than the Standard Model predicts. This connects to Webb's impossible galaxies in a subtle but important way. Modified early expansion dynamics could change which regions of space had the density needed to collapse into the first halos and galaxies, and could alter the timescales involved in ways that make the observed massive early galaxies more consistent with the modified physics. Researchers were careful to note that this remains speculative territory. The Dark Energy Spectroscopic Instrument results required further data collection and analysis before reaching the confidence level needed for firm conclusions. The connection to Webb's galaxy formation problems was suggestive, an intriguing alignment between two independent anomalies rather than a proven causal link. But the alignment was real, and the fact that two entirely separate observational programs, one mapping galaxy redshifts across billions of light years, and one imaging the universe's first galaxies, were both pointing at anomalies in the early universe's physics, was the kind of convergence that keeps physicists awake at night. Among all the surprises Webb pulled from the early universe, the dead galaxies were among the most quietly disturbing. Dead galaxies are galaxies that have stopped forming stars. They appear red, dominated by the light of old, cool stars, their gas supply exhausted or expelled, their star-forming machinery shut down. In the modern universe, dead galaxies are common, particularly among the largest elliptical galaxies, which consumed or expelled their gas billions of years ago. The Standard Model predicted that dead galaxies in the early universe should be rare or absent. Star formation should have been running at full capacity during the universe's first few billion years, driven by abundant gas supplies and the rapid assembly of new structure. A galaxy that died early would require some mechanism to shut off its star formation prematurely, something strong enough to overcome the enormous gas reservoirs available in the early cosmos. Webb found dead galaxies at redshifts that placed them in the universe's first 2 billion years. Massive, well-formed systems that had already completed their entire star-forming lives and gone quiet at a time when the standard model said they should have been in their most active phase. The most extreme case was a galaxy confirmed by Webb in 2024 that had apparently formed the bulk of its stars in a frenzied burst lasting only a few 100 million years, then abruptly shut down, all before the universe reached its first billion years. It sat there, massive and inert, dead before most modern galaxies had even started assembling. The mechanism most commonly invoked to explain early galaxy death is feedback from a supermassive black hole at the galaxy's center. When a black hole feeds at extreme rates, it generates outflows of energy powerful enough to heat and expel the surrounding gas, cutting off the fuel supply for star formation. This quenching mechanism is well documented in the modern universe, where large elliptical galaxies show clear evidence of past quenching events driven by their central black holes. But for quenching to shut down a galaxy in the first billion years requires a supermassive black hole already large enough to generate galaxy-scale outflows at that early time. And that circles back to the problem of early black hole growth. A supermassive black hole capable of quenching an entire galaxy so early must have grown to enormous mass even earlier, in a window of time that strains the physics of black hole accretion all over again. The dead galaxies compounded the timeline problem rather than solving it. Each explanation pointed upstream to an earlier unsolved mystery, like pulling a loose thread and finding it connected to the entire fabric. Some researchers proposed an alternative quenching mechanism: early galaxy-scale mergers so violent that they consumed all available gas in a catastrophic starburst, burning through the entire fuel supply in a single explosive episode. Simulations showed that such events were possible in principle, but reproducing their frequency in the early universe required conditions that again pushed against the standard model's predictions. The dead galaxies sat in Webb's data as mute evidence of lives lived and ended at a pace the cosmos was not supposed to allow, and they carried one more implication, subtle but significant. If galaxies could grow fast enough to die in the first billion years, the entire distribution of galaxy types across cosmic time was more complex than the models had mapped. And that complexity was about to appear in an entirely different form, one that involved collisions so dramatic they rewrote the rules of early cosmic assembly. Galaxies collide. The universe is not a static arrangement of isolated islands. It is a churning, gravitationally entangled system where galaxies move through the cosmic web, pulled toward concentrations of mass, falling into clusters, merging with neighbors. The Milky Way itself is on a collision course with the Andromeda Galaxy, a meeting expected to occur in roughly 4.5 billion years. Mergers are a known part of galaxy evolution. The standard model incorporates them as a key mechanism by which galaxies grow over time. Small galaxies merge into medium ones merge into large ones. The process leaves scars, warped disks, shells of stars stripped from captured galaxies, streams of material pulled loose by tidal forces. The Milky Way carries those scars. Most large galaxies do. The model also predicted the timing of major mergers. In the early universe, when the cosmic web was still forming and galaxies were more spread out and less massive, major mergers should have been relatively rare. The conditions for frequent dramatic collisions were expected to develop gradually as cosmic structure matured and galaxies began clustering more densely. Webb found merger evidence in galaxies so old that the standard timeline had no room for it. One striking example was a system observed at a redshift placing it in the universe's first billion years, showing clear signatures of an ongoing major merger between two massive galaxies. The two components, each already holding enormous stellar masses, were in the process of combining into something even larger. Their interaction was producing a burst of star formation visible in the combined system's light. For two massive galaxies to be merging in the universe's first billion years, both had to have formed and grown to substantial size independently before that merger began. Two impossible galaxies, in other words, colliding to produce something doubly impossible. The merger's star formation rate, driven by the violent compression of gas as the two galaxies interpenetrated each other, was among the highest measured at any point in cosmic history. Gas clouds, compressed by the collision's shockwaves, were collapsing into stars at a rate that made even the extreme rates seen in isolated early galaxies look modest. This suggested that mergers in the early universe, when they did occur, may have been especially productive. The gas fractions in early galaxies were much higher than in galaxies today, since less gas had been consumed by prior star formation. When two gas-rich galaxies collided, the resulting starburst had more fuel to burn, producing more stars more quickly than equivalent mergers in the modern universe would. Some theorists propose that these gas-rich early mergers might be a key part of the explanation for the impossible galaxies. If mergers in the early universe were especially efficient at triggering extreme star formation, a chain of rapid mergers could, in principle, build a massive galaxy faster than the standard model's gradual assembly timeline allows. The challenge was demonstrating that mergers occurred frequently enough and early enough to account for the total stellar mass observed. Current simulations struggled to produce sufficient merger rates of those redshifts without modifying the properties of dark matter or the initial conditions of structure formation. Webb's merger discoveries added a new dimension to the problem. The early universe was actively assembling, violently and rapidly, through collisions the standard model said should have been rare. And somewhere inside the light of those colliding galaxies, researchers were catching the first faint hints of something even more ancient. No one has ever seen a population 3 star. They are the most important stars in cosmic history, and they are completely invisible to every telescope that has ever operated, until now possibly. Webb's reach into the epoch of reionization has placed it closer than any instrument before to the era when those first stars burned, and the hunt for direct evidence of them has become one of the most closely watched searches in modern astronomy. The challenge is fundamental. Population 3 stars lived fast and died young. The most massive among them, potentially hundreds of times the mass of the Sun, consumed their fuel in a few million years. By the time any photons from those stars could reach a telescope today, the stars themselves had been dead for over 13 billion years. Observing them directly means catching their light in the act of traveling, which means looking far enough away that the light is still arriving from a time when they existed. Webb can theoretically see that far. The question is whether individual population 3 stars or clusters of them produce signatures distinct enough to be separated from the combined glow of early galaxies. Most researchers acknowledge that isolating a single population 3 star is probably beyond even Webb's capabilities. The stars are far too distant and too small on the sky to be resolved as individual objects. But population 3 stars in groups might tell a different story. A region of the early universe where population 3 star clusters dominated would produce a very specific radiation signature. Extremely hard ionizing ultraviolet radiation, far more energetic than modern hot stars produce, resulting in unusual emission line ratios in the spectrum of the galaxy hosting them. Webb has detected candidate signals. In several high redshift galaxies, spectroscopic observations have revealed emission line ratios that are difficult to explain with known stellar populations. The helium emission line signature, in particular, a line produced when helium is ionized by extremely hard radiation, has appeared at strengths that push the limits of what modern stars can produce. One galaxy studied in 2023, designated as a high redshift system, but referred to by researchers simply as the candidate, showed a spectral feature consistent with a large population of stars producing radiation harder than any known stellar type. The team that analyzed it published their findings with appropriate caution, noting that alternative explanations including an active supermassive black hole contributing to the radiation field, could not be ruled out. The distinction matters because confirming even one solid population 3 signature would not just answer a question about the early universe. It would confirm a theoretical chain stretching from the Big Bang to every atom of every heavy element in every planet, star, and living being today. Population 3 stars were the first step in that chain. Seeing one, even indirectly, would be seeing the universe's first act of chemical creation. Webb's upcoming observations include dedicated programs targeting the most extreme high redshift systems for spectroscopic analysis specifically designed to detect population 3 signatures. Scientists running those programs describe the search with a restrained excitement that carries the weight of knowing they might be one observation away from the deepest confirmed look into cosmic history ever achieved. Whether those observations succeed or not, the connection between population 3 stars and the galaxies we live inside today runs deeper than most people realize. Every galaxy alive today has a history, a lineage traced backward through mergers, accretion events, and the initial collapse of gas into the universe's first structures. The Milky Way is no exception. Our galaxy contains stars of radically different ages. The youngest, in regions like the Orion Nebula, are forming right now, coalescing from gas clouds that have existed for millions of years. The oldest stars in the Milky Way, found in ancient globular clusters orbiting the galaxy's halo, date back over 13 billion years. They formed when the universe was barely old enough to have produced the first generation of stars. Those ancient halo stars are the Milky Way's living fossils. Their chemical compositions record the conditions of star formation in the very early universe, the mix of elements available in the gas from which they formed, shaped by whatever population 3 stars and early supernovae had already processed before them. Astronomers studying these ancient stars have traced the Milky Way's assembly history backward through their chemical signatures. The picture that emerges is of a galaxy built from many smaller pieces, dozens or possibly hundreds of smaller galaxies and star clusters, captured and absorbed over billions of years. Each captured system added its stars and its chemical signature to the growing whole. This assembly history means that the Milky Way's story stretches back to the very era Webb is now imaging. The small early galaxies and star clusters that eventually merged to form the structures we live inside today were objects like the ones appearing in Webb's deep field images. Some of the galaxies Webb is finding in the early universe are almost certainly direct ancestors of galaxies like ours. That connection carries a striking implication. The impossible galaxies Webb found, the ones forming stars at extreme rates in the universe's first few 100 million years, may not be exotic exceptions. They may be the progenitors of ordinary galaxies today. The Milky Way's own assembly history might include an early phase of extreme star formation, a frenzied beginning that settled into the quiet, moderate star-forming pace we observe now. Some simulations suggest that the Milky Way's ancient halo stars, the ones over 13 billion years old, formed during exactly such a phase. A brief early burst of intense star formation in a small proto-galactic structure, followed by a period of relative quiet as gas supplies were consumed and the galaxy settled into a more mature state. If that picture is correct, the extreme early galaxies Webb is observing are not anomalies in the history of the universe. They are the normal starting point. Every large galaxy in the modern cosmos may have gone through a similar early phase of rapid, intense assembly. That would not eliminate the tension with the standard model, because the models still predict those early phases should have been less extreme than what Webb is finding. But it would place the impossible galaxies in a different context, as the opening chapters of a story that includes our own galaxy, our own sun, and every atom in our bodies. The chain from the Big Bang's first light to the oxygen we breathe runs directly through those ancient, impossible galaxies. They were not outliers in the cosmic drama. they were the opening act. And the stage they performed on, the dark ages of the universe before they ignited, may have been less quiet than anyone assumed. The cosmic dark ages are described in textbooks as a period of silence, after the Big Bang's initial heat faded and before the first stars ignited. The universe sat in a featureless, lightless state, a vast cold sea of hydrogen and helium drifting under gravity. Nothing glowed, nothing was visible. A physicist transported to that era would see absolute blackness in every direction. That description is accurate as far as it goes, but Webb's observations of the era just after the Dark Ages ended are forcing a reconsideration of what was happening during those hundreds of millions of years of darkness. The Dark Ages were not structurally inactive. Gravity never switches off. During the entire lightless period, dark matter halos were forming, growing, merging. Gas was cooling and flowing into those halos. The cosmic web was assembling itself in darkness, building the scaffolding on which the first light sources would eventually ignite. The question Webb's data pushes back toward that dark era is this: how advanced was that invisible assembly when the first stars finally lit up? The answer, hidden in the chemical compositions and stellar populations of the earliest visible galaxies, suggests the answer is more advanced than expected. A galaxy observed at a redshift corresponding to 500 million years after the Big Bang, already old and chemically enriched, implies that star formation during the Dark Ages or immediately following them was far more vigorous than the standard picture assumed. The Dark Ages may have ended not with a gradual trickle of first stars, but with a rapid surge of star formation across multiple regions simultaneously. Evidence for this comes from the distribution of reionization itself. Webb's imaging of the reionization epoch shows that the hydrogen fog was cleared in patches, with some regions becoming transparent much earlier than others. Those early clearing regions correspond to the locations of the densest early galaxy concentrations. Dense galaxy clusters in the early universe producing enormous amounts of ionizing radiation collectively could punch large holes in the surrounding hydrogen fog long before isolated galaxies managed the same. That patchy reionization implies that the density contrasts in the early universe were large, regions with many early galaxies grouped closely together, and regions with far fewer. The standard model predicts density contrasts existed, but the amplitude of those contrasts, how extreme the differences were between dense and sparse regions, may have been larger than the models assumed. Larger density contrasts in the early universe would mean that structure formation happened faster in the densest regions, producing the first galaxies earlier and more efficiently than uniform models predict. It would also mean that the Dark Ages in those dense regions effectively ended sooner, with local reionization completing before the global average. Mapping this early patchiness across larger areas of sky is one of Webb's primary ongoing scientific programs. Each new deep field image adds data to that map, and each addition refines the picture of how structurally complex the Dark Ages actually were. The universe's silent era was apparently building something far more elaborate than its stillness suggested. And the revelations about that era fed directly into a debate that had been simmering in cosmology for years, a debate about whether the entire theoretical framework needed small adjustments or a fundamental replacement. Every scientific crisis reaches a fork. At one path, the existing theory absorbs the new data through targeted modifications, specific adjustments that preserve the overall framework while addressing the anomalies. Down the other path lies a more radical option. The existing theory is replaced by something structurally different, something built to explain both the old successes and the new failures simultaneously. Cosmology stood at that fork in 2024, and the debate about which path to take was neither polite nor fully resolved. The defenders of modification made a strong case. The Lambda CDM model has an extraordinary record. It accurately predicted the spectrum of temperature fluctuations in the cosmic microwave background before those fluctuations were measured. It predicted the large-scale distribution of galaxies before surveys mapped them. It correctly described the universe's accelerating expansion and the approximate ratios of dark matter, dark energy, and normal matter. Throwing out a theory with that track record requires overwhelming evidence, and the Webb anomalies, while serious, remained concentrated in a specific regime of redshift and mass. Proposed modifications circulated widely, adjusted initial mass functions for early stars, modified dark matter properties at early times, improved treatment of feedback processes in galaxy formation simulations, enhanced gas cooling rates driven by early magnetic fields or cosmic rays. Each modification was constrained to be as minimal as possible, targeting only the specific failure points while leaving the broader model intact. The challenges of the framework were less accommodating. Several researchers pointed out that the list of modifications required to accommodate Webb's data had grown long enough to raise a different concern. At what point does a theory with enough modifications become a different theory? The Lambda CDM model with radically different dark matter properties, modified early expansion dynamics, and altered star formation physics was not obviously the same framework anymore. Some proposed replacing the cold dark matter component with alternatives. Fuzzy dark matter, a model in which dark matter particles are so light they behave as quantum waves rather than point particles, produces smaller scale structure in the early universe and might naturally suppress the formation of small halos while enhancing the formation of large ones in dense regions. Whether that enhancement is the right kind to explain Webb's galaxies was an open calculation. Others went further and questioned the cosmological constant. The Hubble tension, the discrepancy between different measurements of the universe's current expansion rate, had been building as an independent problem for years before Webb launched. Some physicists argued that the Hubble tension and Webb's galaxy formation anomalies were symptoms of the same underlying issue, a cosmological model that correctly described the universe at some epochs and some scales, but had a flaw embedded in its foundations that revealed itself only at the extremes. The scientific community had not resolved this debate. No resolution was imminent. The data was real, the tension was real, and the path forward required more observations, more theoretical work, and more of the patient, contentious process through which science actually moves. And the tool for gathering those observations, Webb itself, was only partway through its scientific program. The telescope was designed for a 10-year primary mission, and the data from its first 2 years had already shaken the foundations. Years 3 through 10 promised to push even further. The James Webb Space Telescope's primary mirror is a marvel of engineering so specific in its requirements that building it took over 2 decades. The mirror consists of 18 hexagonal segments, each one made of beryllium, a metal chosen for its extraordinary stiffness to weight ratio and its stability at the cryogenic temperatures of space. Each segment is coated with a layer of gold roughly 1,000 atoms thick, thin enough to apply without adding significant mass, but sufficient to maximize infrared reflectivity. Gold reflects infrared light more efficiently than any other coating material. Each segment is also independently adjustable. Tiny actuators on the back of every hexagon can tilt and shift the mirror to sub-nanometer precision, a precision smaller than the wavelength of visible light itself. After Webb deployed in space, the team spent months precisely aligning all 18 segments until they functioned as a single unified mirror, 21 feet across. The alignment process required adjusting each segment's position and orientation through iterations measured in billionths of a meter. The result is a light collecting area roughly 6 times larger than Hubble's. That scale difference translates directly into sensitivity. Webb can detect objects roughly 100 times fainter than Hubble could, and it can detect them in the infrared wavelengths where the most ancient light in the universe arrives, after being stretched by cosmic expansion. The telescope carries 4 primary science instruments, each optimized for specific observations. The near-infrared camera captures images with extraordinary resolution across the infrared band, where most high-redshift galaxies emit their light. The near-infrared spectrograph can simultaneously take spectra of up to 200 objects at once, a multiplexing capability that dramatically accelerates the work of confirming galaxy distances. The mid-infrared instrument covers longer infrared wavelengths, reaching the most heavily redshifted light and detecting dust emission in early galaxies. The fine guidance sensor and near-infrared imager stabilize the telescope to extraordinary precision and provide additional imaging capability. Together, these instruments give Webb a capability that no previous observatory possessed: the ability to simultaneously image and spectroscopically characterize hundreds of galaxies across a wide range of redshifts in a single long observation. A single Webb pointing at a deep field produces data that would have required dozens of separate Hubble observations across multiple years, and even then Hubble could not have reached the redshifts Webb routinely covers. The sun shield that protects Webb from thermal contamination is itself an engineering achievement. 5 layers of a material called Kapton, each layer thinner than a human hair, coated with aluminum and silicon, deployed in space to cover an area the size of a tennis court. The temperature difference between the sun-facing side of the shield and the mirror side exceeds 560 degrees Fahrenheit. Without that shield, Webb's own thermal emission would overwhelm the faint infrared signals it is hunting. All of this precision exists in service of answering questions about the early universe. The specific decisions made in Webb's design, the mirror size, the infrared optimization, the sun shield, the spectroscopic multiplexing, were driven by the scientific goals of observing the first galaxies. The impossible galaxies it found were always the target. The surprise was that they turned out to be so much more extreme than anyone anticipated. And between Webb's mirror and those ancient galaxies, one more physical phenomenon was doing unexpected work. Albert Einstein predicted it over a century ago, and astronomers have been exploiting it ever since. Massive objects bend space, and bending space bends light. When a galaxy cluster, or any sufficiently massive structure, sits between Earth and a more distant object, the gravity of that intervening mass warps the surrounding space-time. Light from the distant object, traveling through that warped region, follows curved paths around the mass. From a telescope's perspective, the distant object appears magnified, distorted, sometimes split into multiple images, arranged in arcs around the lensing mass. The effect is called gravitational lensing, and the massive structure producing it is called a gravitational lens. For observational astronomy, gravitational lensing is a gift. It provides magnification that no engineered telescope can match. The most powerful gravitational lenses can amplify the light from background objects by factors of 10, 50, or even 100, bringing objects into view that would otherwise be far too faint to detect. Webb uses gravitational lensing deliberately. Several of its deep field programs target known massive galaxy clusters specifically because those clusters act as natural magnifying glasses for whatever lies behind them. The cluster's gravity bends and amplifies the light of far more distant galaxies, making them accessible at levels of detail impossible to achieve from a direct view. Some of the most extreme high redshift galaxies confirmed by Webb were detected precisely because a foreground cluster amplified their light enough to reveal spectroscopic features that would otherwise have been undetectable. The mass of intervening clusters built up over billions of years became a tool for seeing deeper into the universe's past. The lensing effect also produces characteristic distortion patterns, circular arcs, elongated streaks of light, mirror images of the same distant galaxy appearing multiple times around the lensing mass. These distortion patterns allow astronomers to calculate the total mass of the lensing structure including the invisible dark matter component, by measuring exactly how much the light is bent. Webb's precision imaging has made this mass mapping extraordinarily detailed. In some lensing clusters, the dark matter distribution can be mapped at resolutions revealing structures within the dark matter halo that previous telescopes could only approximate. Those maps are contributing to independent tests of dark matter properties, adding yet another layer to the broader investigation of what the early universe's physics actually looked like. Gravitational lensing also carries a limitation that Webb's teams work carefully to account for. A background galaxy that appears large and bright due to lensing magnification can be mistaken for a genuinely large and bright object if the lensing effect is not correctly identified and subtracted. Early in Webb's mission, some high redshift galaxy candidates were reclassified after detailed analysis revealed that gravitational lensing was amplifying objects smaller than initial estimates suggested. The careful accounting for lensing in Webb's impossible galaxies was one of the first things researchers checked when the massive early galaxy candidates appeared. In most cases, the lensing contribution was minor, and the fundamental mass estimates held. The galaxies were genuinely impossible, with or without nature's extra magnification. But magnification was not the only thing helping Webb see what previous telescopes had missed. The sheer number of anomalous objects accumulating in its datasets was also telling a story, one with statistical implications that shifted the entire conversation. A single anomalous galaxy is a curiosity. Scientists call it an outlier, check for measurement errors, add it to a list of objects requiring further study, and move on. The standard model has always accommodated individual oddities. Observations are imperfect. Data has noise. The universe is large enough that improbable events occasionally occur. When the anomalous galaxies became dozens, the conversation shifted. Statistical outliers exist in every dataset, but outliers clustered around the same specific properties, the same redshift ranges, the same mass scales, the same apparent violation of the same theoretical prediction, stopped being outliers and started being a pattern. By mid-2024, Webb's accumulated data on high redshift massive galaxies had grown from a handful of striking individual cases to a catalogue running into the hundreds. Multiple independent teams, working from different Webb programs, targeting different regions of sky, using different analysis pipelines, were finding the same class of object at the same impossible mass scales. The statistical significance of the discrepancy between those observations and the standard model's predictions had grown to the point where the language of scientific papers began changing noticeably. Early papers used hedged phrasing, tension with predictions, challenging to explain within current models, further data required. Later papers were less deferential, inconsistent with lambda CDM predictions, requires modification of the standard framework, and in some cases, fundamental revision of galaxy formation theory may be necessary. That escalation in language reflects how statistical significance works. One galaxy at an impossible mass is a 1 in 1,000 chance, something the model can survive. 10 galaxies at impossible masses is 1 in 10 billion, harder to explain away. Hundreds of galaxies across independent surveys at consistently impossible masses is a number so small it ceases to be a meaningful probability statement and becomes simply, the model is wrong in this regime. The regime in question was specific. Galaxies above a certain mass threshold at redshifts above about 8, corresponding to the universe's first billion years. Below that redshift, the standard model's galaxy mass predictions matched Webb's observations reasonably well. Above it, the prediction systematically underestimated the number and mass of observed galaxies. That boundary is itself a scientific clue. Something was different about the universe's first billion years compared to later epochs. Something that allowed galaxies to grow faster and more massive than the model accounts for, whatever that something was. It operated at early times and then apparently faded, producing a universe at moderate redshifts that looks more or less as expected. A mechanism that was more active early than late, and that specifically enhanced galaxy growth in the first billion years, sounds like a description of something tied to the universe's initial conditions. The specific physics of the Big Bang, the properties of the primordial fluctuations that seeded all structure, or the behavior of matter and energy in those first extraordinary moments. That path led back to fundamental cosmology and to a question that sat beneath all the galaxy formation problems. Was the Big Bang itself different than the model assumed? The Big Bang is the most tested event in the history of science. The cosmic microwave background, the faint glow of radiation left over from the universe's hot, dense beginning, has been measured by multiple satellite missions with extraordinary precision. Its temperature pattern across the sky, a map of tiny density fluctuations from the universe's first 380,000 years, matches the predictions of inflationary cosmology to a degree that leaves little room for major deviations in the standard picture. Inflation is the theory that in the universe's first tiny fraction of a second, space expanded at a rate far exceeding the speed of light, stretching quantum fluctuations to cosmic scales and setting the initial conditions from which all structure grew. The predictions of the simplest inflationary models match the cosmic microwave background data so well that inflation is broadly accepted as the correct framework for the universe's very beginning. But inflation is a broad class of theories, and different inflationary models make subtly different predictions about the statistical properties of the initial density fluctuations, the amplitude of those fluctuations, their distribution across different scales, and their statistical properties can vary between models, and those variations can affect how structure forms in the universe's first billion years. Some researchers began examining whether specific variants of inflation could produce initial conditions that led to faster early galaxy formation than the simplest models predict. Inflation models that produce a slight excess of power on small scales, meaning slightly larger density fluctuations at the scales relevant to galaxy formation, would create more overdense regions that could collapse into galaxies earlier and more efficiently. Such models existed before Webb launched. They were considered theoretically interesting but observationally unconstrained. Webb's data gave them a new context, a potential observational motivation that had previously been absent. The connection between inflation and Webb's impossible galaxies is indirect and requires several steps of theoretical reasoning to establish. But the reasoning is internally consistent, and several papers exploring it appeared in peer-reviewed journals in 2023 and 2024. None claimed to have solved the problem. All presented the idea as a viable direction worth exploring with more data. The cosmic microwave background measurements constrain these modified inflationary models tightly. And so far, no variant that dramatically changes early galaxy formation has been found that also fits the microwave background perfectly. The constraints are not absolute, since measurement precision has limits, and future experiments planned to map the microwave background with even higher resolution might reveal subtle signatures of modified initial conditions. The possibility that the Big Bang's details, the specific form of inflation, the specific amplitude of initial fluctuations, the specific properties of whatever exotic field drove the inflationary expansion, could explain Webb's impossible galaxies is genuinely exciting to cosmologists. It would mean the telescopes were not finding a problem with galaxy physics. They were finding a signal from the universe's very first moments, information about conditions so extreme and so brief that they lasted only a fraction of a second. Reading the universe's origin story in the light of ancient galaxies would be one of the most extraordinary achievements in the history of science, and determining whether that reading is correct would require understanding something about the scale of what Webb had revealed and what it meant that ordinary models had missed it so completely. Scientific frameworks do not fail all at once. They erode. A small anomaly appears, gets absorbed with a minor modification. Another appears, requires a slightly larger fix. Over time, the modifications accumulate until the framework's original elegance is buried under layers of correction. At some point, a new theory that explains everything cleanly becomes more economical than the old theory held together with patches. This was the pattern with Newtonian gravity. Newton's laws worked extraordinarily well for over 2 centuries. They explained planetary motion, the tides, the trajectories of cannonballs. Then measurements became precise enough to reveal tiny deviations in Mercury's orbit that Newton's laws could not account for. Physicists tried modifications. None worked cleanly. Einstein's general relativity came along and explained Mercury's orbit precisely, along with everything Newton had explained, without any patches at all. The lambda CDM model was not at the Newton stage. Its defenders were right about that. The core of the framework, dark energy driving expansion, cold dark matter anchoring structure, the Big Bang as the origin point, remained consistent with the vast majority of observations. Webb's anomalies were real, but confined to a specific regime. However, the relevant historical lesson was not that Newton was suddenly wrong everywhere. It was that the place where his framework first visibly failed pointed to something deeper. Mercury's orbital anomaly, which seemed like a small technical problem, turned out to be a symptom of general relativity lurking beneath Newtonian physics, a more fundamental description of gravity that contained Newton's laws as a special case. Cosmologists discussing Webb's findings in that context were asking a parallel question. Was the early galaxy problem a symptom of something deeper lurking beneath the standard model? A more fundamental description of dark matter, dark energy, or cosmic structure that contained lambda CDM as a special case valid at later times and moderate scales. But that revealed new physics at the extreme scales of the early universe. If the answer was yes, the consequences would extend far beyond galaxy formation. A more fundamental cosmological theory that replaced lambda CDM would likely change the picture of the universe's ultimate fate, the nature of dark matter and dark energy, and possibly the interpretation of the Big Bang itself. Entire fields of theoretical physics connected to the standard cosmological model would require re-evaluation. The scientific community was not in a position to make that declaration based on the existing data. The Webb anomalies were serious. They were not yet conclusive. But the trajectory of the evidence, the fact that more data consistently deepened the tension rather than resolving it, was giving a growing number of researchers pause. The question of what falls with the standard model, if the standard model falls, was one that theorists were beginning to take seriously enough to publish. And the answer involved structures in the universe far larger than any galaxy, structures that the early universe anomalies were beginning to connect to in ways that nobody had quite anticipated. The observable universe is a sphere roughly 93 billion light-years across. Every galaxy, every star, every atom of matter we have ever detected sits within that sphere. Beyond its edge, light has not had time to reach us since the Big Bang, so we can observe nothing past that boundary. The edge of the observable universe is not a wall. It is a horizon defined by time and the speed of light. Within that horizon, the universe appears broadly uniform at the largest scales. The cosmic microwave background is remarkably smooth, varying by only 1 part in 100,000 across the entire sky. Galaxy distributions averaged over large enough volumes look similar in every direction. The universe appears, at its grandest scale, statistically homogeneous, the same everywhere, the same in every direction. Cosmologists call this the cosmological principle. The cosmological principle is not directly tested at scales smaller than a few billion light-years. because observational surveys have not yet mapped the full universe at finer resolution across the entire observable volume. And in the regions that have been surveyed, some structures have appeared that strain the principle at its boundaries. The Hercules Corona Borealis Great Wall, a concentration of galaxy clusters spanning roughly 10 billion light-years, is one such structure, according to the Standard Model's cosmological principle. Structures of that scale should not exist. The model predicts that density variations at such large scales should have been smoothed out by cosmic expansion long ago. Yet the structure is there, confirmed by multiple independent observations, sitting in the data as another anomaly waiting for an explanation. Webb's impossible early galaxies connect to this large-scale structure problem through a subtle but direct link. If the early universe had larger density fluctuations than the Standard Model predicts, those fluctuations would produce not only more vigorous early galaxy formation in dense regions, but also larger large-scale structures in the present-day universe. A single modification to the initial conditions, larger primordial fluctuations at specific scales, could potentially explain both Webb's early galaxy anomalies and the existence of structures like the Hercules Corona Borealis Great Wall. That connection, if verified, would mean the anomalies are not isolated problems in different corners of cosmology. They are facets of the same underlying departure from the standard picture, a universe whose initial conditions produced slightly more structure at every scale than the simplest models assume. The observable universe might be showing us the footprint of something beyond its own boundaries. If the universe is infinite, or even just dramatically larger than our observable sphere, then the specific patch we inhabit might be statistically unusual in ways that produce the anomalies we measure. An overdense region of a much larger cosmic structure, for example, would host more early galaxy formation and more large-scale structure than the universe's average. This possibility, called cosmic variance by cosmologists, is acknowledged but difficult to test. By definition, we cannot observe beyond our own horizon to check whether our local patch is typical. It remains a theoretical consideration rather than an actionable hypothesis. What Webb was doing, week by week, was mapping that local patch in more detail than ever before, and each new detail was pointing in the same direction. The James Webb Space Telescope was designed for a 10-year primary mission, with enough fuel for at least 20 years of operation. The launch in December 2021 was so precise that far less fuel was consumed during the journey to Lagrange Point 2 than the worst-case estimates required. Webb will operate for longer than originally planned, possibly well into the 2040s. In that time, the telescope's scientific programs are structured to systematically address the exact questions its early data raised. The anomalies of the first 2 years were, in a sense, the discovery phase. The years that follow are the investigation phase, designed to understand what was found and why. Several specific programs are already approved and underway. The first targets the epoch of reionization, with the goal of mapping the three-dimensional distribution of early galaxies across large enough areas of sky to measure the statistical properties of galaxy clustering at high redshift. Comparing that clustering to the predictions of different dark matter models will test whether cold dark matter, warm dark matter, or fuzzy dark matter better explains the observed structure. Results from this program, expected across the next several years, will either support or challenge the dark matter modifications proposed in response to the impossible galaxies. A second program focuses on spectroscopic confirmation of the highest redshift galaxy candidates, the objects at redshifts above 15 that currently rest on photometric estimates alone. Confirming their distances with the precision of spectroscopy will determine whether the most extreme end of Webb's galaxy catalogue reflects reality or measurement uncertainty. Each confirmed object at those extreme distances adds weight to the case for modified cosmology. The third is the population 3-star search, Dedicated spectroscopic observations of specific high-redshift galaxies, selected for their unusual emission line properties, will attempt to definitively identify or rule out the presence of population 3, stellar populations. A confirmed population 3 signature would be among the most significant astronomical discoveries in decades, directly confirming the theoretical chain from Big Bang to modern chemistry. The fourth program involves combining Webb observations with those from other next-generation instruments. The extremely large telescope, currently under construction in Chile, will be capable of ground-based spectroscopy at resolutions that complement Webb's space-based imaging, allowing joint observations that address questions neither telescope can answer alone. The Nancy Grace Roman Space Telescope, planned for launch in the late 2020s, will survey far larger areas of sky in infrared wavelengths, providing the statistical sample sizes needed to transform Webb's individual discoveries into population-level measurements. The Euclid Space Telescope, launched in 2023 and now operational, is mapping hundreds of millions of galaxies across a wide range of redshifts, providing the large-scale structure context into which Webb's early galaxy discoveries fit. Joint analysis of Euclid's wide-field data and Webb's deep-field data is already producing papers and will produce many more. The scientific program taking shape around Webb's discoveries is arguably the most ambitious coordinated effort in observational cosmology's history. Multiple space telescopes, multiple ground-based observatories, and theoretical groups on every continent are all focused on the same questions Webb raised in its first 2 years. The answers, when they arrive, will either confirm that the standard model needs targeted modifications or reveal that the universe's early history operated by rules still waiting to be written. Either outcome changes the field permanently. When Webb sent back its first images, most people looked at them and felt wonder. The sheer number of galaxies, the depth of the field, the age of the light. It was visually overwhelming and emotionally resonant in a way that scientific imagery rarely achieves. But underneath the visual beauty was something that should disturb us in a more productive sense. The images revealed that our mental model of the universe, the story we tell ourselves about where everything came from and how it grew, is incomplete in ways we had not measured until now. The standard cosmological model is not a casual guess. It is the product of thousands of scientists working across generations, building mathematical frameworks, running observations, comparing predictions to data, refining their understanding in the most rigorous process humans have ever developed for learning about reality. And that process produced a model that correctly describes enormous amounts of what we see. The humbling fact is that it still got the early universe wrong, or at least it got it incomplete. The galaxies Webb found sitting in cosmic infancy, already massive, already chemically complex, already in some cases already dead, are telling us that something was happening in those first few 100 million years that our models did not capture. That incompleteness matters beyond the professional concern of cosmologists. The story of the early universe is the story of how everything began, of how matter organized itself out of the featureless chaos of the Big Bang into the complex structures, including planets, oceans, biology, and consciousness that exist today. Every element in every cell, in every living thing, traces its origin through a chain of stellar processes that began with those first impossible galaxies. If we have the early chapters of that story wrong, we have the foundation wrong. And building a complete understanding of reality on an incomplete foundation means that somewhere down the line, in some domain of science or technology or human knowledge we cannot yet predict, the gap will matter. The discovery Webb made is not a failure. Discovering that a theory is incomplete is exactly how science is supposed to work. A model that cannot be proven wrong by evidence is not science. A model that breaks against new data, then gets rebuilt, then breaks again and gets rebuilt better. Is science at its most alive? The astronomers and physicists working through Webb's data right now are doing something that matters beyond their field. They are sitting with genuine uncertainty, running the calculations again, publishing papers that disagree with each other, testing hypotheses against new observations, and refusing to accept an answer just because it is convenient. That process, disciplined, rigorous, argumentative, and ultimately honest, is the closest thing humanity has to a reliable method for understanding how the universe actually works. The early universe formed galaxies that should not exist. Webb found them. The models are being rewritten, and somewhere in the data Webb is gathering right now, in a spectrum or a deep field image or a statistical pattern not yet analyzed, the answer is already there, waiting to be read. The universe has been trying to tell us its real story. We are finally close enough to hear it.